Hi, I'm Shashwat Pathak. I'm an undergraduate in the Department of Electrical Engineering at IIT Tirupati, and today I'll be talking about fringe projection profilometry. So let's get started.
The research paper I referred in order to make this presentation is Characterization of Color Crosstalk of Color Coupling Devices and its Influence in Multispectral Phase Imaging. This research paper was published in 2019 in the OSA conference.
Every day, we come across a number of 3D objects. The methods involved in acquiring a spatial feature like its shape are very involved and requires knowledge of advanced concepts in signal processing and computer vision. The recent advancements in 3D printing are a result of developments done in the shape measurement techniques. Before coming to color fringe projection profilometry, I would like to give an overview of what fringe projection is and the steps involved in it. Fringe projection is a method of 3D shape measurement in computer vision, which involves measurement using structured light and is among the most popular techniques in the optical metrology community. The standard vision based methods are based on stereoscopic vision and other contact based methods, the one through which we see. But this method is more accurate and can be leveraged for microscopic applications too. Other methods are contact based and don't have very wide applications. Another application where fringe projection beats conventional methods is with moving objects. Often we are faced with challenges where there is a need to measure the shape of the deformable or moving 3D object. It is highly inconvenient to use any of the contact based method under these circumstances. Even stereo does not give good results. So we need to come up with something which is fast, does not involve contact, and is accurate. That's why we go for fringe projection profilometry. Let's take a look at the processes involved in fringe projection profilometry. There are overall four steps which are involved in this. So the first one being projection and image acquisition. Second is fringe analysis. Third one phase unwrapping, and the fourth one is calibration. The following explanation is given, keeping color fringe projection in mind. Still, these processes are common for any structured light method for shape measurement. Now let us discuss each of these processes one by one. The first step in getting the shape of the object under inspection is to project the fringe pattern on the image and get the deformed fringe pattern. This is the most important process because all the subsequent processes are largely dependent on how well we capture the deformed pattern. Factors such as surrounding light, exposure time, etc. are involved in to get a good snapshot. Thus, it usually takes a lot of time to get the perfect deformed images so that they can go into the data set. Now, in the next image, we'll see. Now, this is how a basic FPP setup looks like. Here, IP is the projected intensity. Alpha times IP is the reflected intensity recovered by the camera. Beta 1 and beta 2 are the ambient light and the reflected light respectively. Now, let us take a simpler analogy to understand this easier. If you're in a class and you see someone standing between the projector and the white screen, intercepting the projection, you might have observed that the pattern of projection on his body is not the same as the one projected on the white screen behind him. This change in pattern occurs because of the 3D profile of the person. Thus, by measuring the deformation in the projected pattern, we can somehow trace back to the depth and other spatial properties of the object. So, this is the main intuition behind fringe projection profilometry is that based on the some spatial characteristics of the object, some deformation is taking place into the fringes, and we're trying to trace back to the shape of the object by analyzing those deformations. Now let's take a look at the next step, fringe analysis. There are four widely used fringe analysis techniques: phase shifting profilometry, Fourier transform profilometry, wavelet transform profilometry, spatial filtering profilometry, etc. The depth and other spatial information is encoded in the phase spectrum of the image. Since the camera only captures the intensity spectrum, thus we cannot measure the spatial characteristics from a single image. But once we have the deformed fringe pattern image, using fringe analysis methods, we can estimate the phase distortion of the original sinusoidal pattern caused by the object with respect to the reference fringe. Now, this is what we basically do in fringe analysis. So, in conventional methods, phase shifting profilometry was used, where multiple phase shifted patterns are projected onto the object, and superimposing the three deformed patterns, the raft phase map of the image was estimated. So what we are going to study mostly is color fringe projection. So the approach is more or less same in color fringe projection also, except as that we do the same thing. Instead of explicitly projecting three phase shifted patterns one at a time, we project three color patterns encoded into a single color fringe only once. Thus, by estimating and superimposing the deformation caused by the object in each color pattern, we can get the wrapped phase map of the images. Now, once we have obtained the wrapped phase map, now it's time to do the phase unwrapping. So to get the true phase from the wrapped phase map obtained after fringe analysis, an unknown multiple of pi is supposed to be added to the wrapped phase map. Now, what multiple of pi is to be added? This is determined using estimation algorithms like Pearl's, Goldstein's, ZPIM algorithm, etc. In color fringe projection profilometry, the most widely used phase unwrapping algorithms is Pearl's, which stands for phase estimation using adaptive regularization based on local smoothing. Now, the unwrapped phase obtained after unwrapping contains both shape related phase and carrier related phase. Thus, it is imperative to have a method to remove the carrier related phase. Normally in various fringe projection techniques, this removal of carrier phase is done by the phase unwrapping algorithm itself. So it gives us the unwrapped phase corresponding to the uh, uh, shape related phase only. Thus, in color FPP, this method is different. Like instead of estimating phase by phase shifting profilometry, we use other methods like Fourier transform profilometry. Now, remember when I discussed the previous methods, like there were four of them in the fringe analysis, we have seen there are four methods, right? So we can use Fourier transform profilometry as well, which we widely use in color fringe projection. Now, what the speciality in Fourier transform profilometry is that the low pass filtering ensures that the carrier phase is removed before we obtain the wrapped phase map. Thus, this method is more reliable when we are measuring shapes of static objects in good lighting conditions, since the wrapped phase map is determined from the single snap itself. While using Fourier transform profilometry, we don't have to explicitly remove the carrier phase map using some phase unwrapping algorithm. So we can remove it through simple processing itself. Now, furthermore, the details of fringe projection profilometry using Fourier transform profilometry will be discussed once we start color projection. Now, since we have obtained the unwrapped phase map corresponding to each pixel in the image, now we'll use the principle of triangulation to map the unwrapped phase map information into the 3D point cloud. The 3D cloud gives us a good estimation of the 3D shape characteristics of the object. It moreover looks like the 3D model of the object under study, which we will see shortly. Now, this slide represents what the principle of triangulation is. So the principle of triangulation is what helps us in getting the depth estimation from the unwrapped phase map. If we know the distance d between the camera and the distance from the projector along with the projection angles, then we can find the depth of the object by finding the unwrapped phase map and finding the difference from the wrapped phase map corresponding to these distances. So using this we can estimate the height h, and that is what our objective is. Now after once we have obtained the point 3D point cloud, that is what actually our objective was. Now here you can see there are three images: test image, ground truth, and unit. Now the ground truth is what is generated with the help of fringe projection profilometry. So the unit is a neural network approach which is trained to give a 3D point cloud from the wrapped phase map. Apart from signal processing techniques, some machine learning techniques also give reasonably good depth construction but require large data sets. The fringe projection method is still more reliable and is used to get the ground truth reconstruction on which the machine learning models are developed. Now that I have given you an overview of what fringe projection is, I'd like to extend our discussion to color encoded fringe projection. Now, what was the need for color fringe projection? Now, it arose because we wanted single shot shape measurement techniques which are fast and more robust to moving objects. Previously, we used to use phase shifting profilometry, in which multiple snapshots need to be taken, and that was more time consuming, and normally it used to give us errors because of the time lag and other acquisition parameters and other acquisition errors were there. Thus, color FPP imitates three-step phase shifting profilometry by projecting three separate color fringe patterns encoded in one single color fringe. By analyzing each of the color channels independently, we can find the wrapped phase map, which can then be forwarded for the subsequent processes. Now, though this method is more quicker and faster, but there is a trade-off for the reliability of this method compared to phase shifting profilometry. The use of color fringes has its own issues like color coupling and imbalance error. Now, what is color coupling? Color coupling is the overlap of one color fringe with other color fringes, providing no fine boundary for separation of channels. Like if you have a color fringe pattern and the red and blue fringes are kind of overlapping, then like normally you can't see there is no fine boundary between the red fringe and the green fringe. Like there is some overlap between both the fringes. Now because of this overlap, the phase estimation is incorrect, so it leads to phase reconstruction error and other things also. Now what is the major cause for this color coupling? Projectors and cameras are usually designed to have some overlap with the spectra of color channels to avoid colorblind regions in the spectrum. Now this unfortunately causes color coupling. This also causes errors in decoding the color fringe into separate patterns, which ultimately leads to incorrect reconstruction of the object under consideration. The color imbalance problem is related to the nonlinearity effect of the cameras and the projectors as well, since the three color channels have different intensity ratios and not compensated directly. Now, why is there a different intensity ratio corresponding to each channel? Since our human eyes have different sensitivity to different colors, most of the projectors are designed to have different intensity responses for RGB colors. Now, these different intensity ratios lead to phase errors. So this error is introduced into a wrapped phase map. And why so? Like the normally what we see, since in a natural surrounding, green is the most dominant color. That's why projectors and cameras have a higher spectral value corresponding to the green channel than for the red or blue channel. That's why the weightage for each different channel is different for different channels, and this leads to reconstruction errors when we are trying to separate them and trying to determine the phase distortions corresponding to each fringe pattern. Now this figure illustrates the effect of color coupling and imbalance error. The first image is the red sinusoidal fringe pattern and the last is the green one. As we can see in this example, the intensity of the red pattern is more than the green pattern. This causes incorrect phase mapping of the pixel corresponding to each channel. Now this is what the now this now this is what the imbalance error is. So due to color coupling, the some phase of one channel gets added to another, which leads to incorrect phase map. So here, what is supposed to be a part of the red phase might get added into the green phase, and so the ultimately the green phase will not be the actual green phase; it will be some part added to it. So this leads to errors in in the final reconstruction when we are trying to superimpose and trying to obtain the unwrapped phase map. So we'll get an errored one because of this color coupling. Another problem with color fringe projection profilommetry is when the color of the object interferes with the color of the projected fringe patterns. To solve this, a complementary color encoded fringe projection method is proposed, in which the complementary fringe pattern is projected on the image to prevent any overlap between the object color and the fringe pattern. The complementary fringe pattern is obtained by subtracting the fringe pixel intensity from 255. So if you have some RGB or any color fringe pattern with you originally and you want to get the complementary fringe, then corresponding to each fringe intensity or its color encode, you have to subtract 1 minus 255 and that will give you the complementary color fringe pattern. Now, the phase calculation method for color FPP is much different from what we saw earlier for phase shifting methods. Here there are the entire process is divided into two parts: primary phase extraction and phase unwrapping. Now let's take a look at the first part, primary phase extraction. From the equation we can see that the phase part phi of x comma y is embedded in the distorted fringe pattern equation. The order to get the wrapped phase map, we take a one-dimensional Fourier transform of the distorted phase map and then shift it back to its central component using a low-pass filter. We can filter out the wrapped phase map from there. The value of f is determined in the calibration process itself. That's why, since we assume that the geometric relationships between the projector and the camera are stable, so we assume this that while we are taking the picture, none of these things are actually the entire setup is stationary. So with this, we assume that the frequency or the f value remains the same, and thus it's predetermined. So that's what we use in order to shift it back to zero frequency, and whatever is left, that is the phi. Now the band pass filter is centered with at the predetermined fundamental frequency f and is extended to both sides of the fundamental frequency using inverse Fourier transform to retrieve the phase distribution of the distorted sinusoidal fringes and getting the wrapped phase map. Now let's look at the second part of this process, phase unwrapping. Now before projecting the fringes, normally since in the color fringe projection, the order of the fringe is very important. Thus it is encoded with a gray code to determine the fringe order, and this gray code is actually necessary to precisely map each pixel corresponding to the phase distortion caused in the deformed fringe pattern. Now normally since there a multiple color fringe might be repeated after a certain interval, so the pixel corresponding to that the pixel in the deformed fringe corresponding to that fringe might not be the same corresponding to some other color fringe, right? So we need to independently identify these fringes apart from their colors as well. So we do this by assigning each fringe a certain gray code fashion, such that we determine, okay, this fringe was there, and correspondingly we can map each pixel uh, back to its original point using the unwrapped phase map. Now the segmentation of the captured pattern as a gray code into separate RGB channels is done by converting them into binary intensities, where 255 corresponds to 1 and 0 corresponds to 0. So it's basically the pixel intensities are binarized in order to segment the captured patterns. Now, this picture above is a demonstration of how color fringe projection works as a three-step phase shifting profilometry. So there you can see this image under the patch under consideration can be seen in the B part, and each of the color fringe deformation is obtained in the A color fringe. Each of the channels are separated, and since all these are phase shifted in certain manner, thus we analyze them from different the warped phase from our channel. Each of the warped phase from each of the A, B, and C channel is obtained from A. You can see in the black and white region. So once you have the warped phase from A, B, and C channel, we can superimpose those in order to get the absolute phase map by adding a certain multiple of pi. That's the typical phase unwrapping process that we discussed. Now, like I discussed, there are limitations due to color coupling and imbalance error on the reliability of the color fringe projection method. And it's not just that the color coupling and that the projector only has issues. There are issues in the standard cameras also, the 3 CCD and 1 CCD cameras, which make them sensitive to color crosstalk. This color crosstalk is nothing but the effect of the color coupling. Thus, measurement and characterization of crosstalk is important so that we can come up with a compensation model or removing the effect of color coupling or color crosstalk. So, it is necessary to take into account and correctly quantify this overlap of fringes in order so that we can model that in form of another function and remove it from our measurements. Now, there are three methods devised to measure the color crosstalk, which are spectral response curves, direct intensity measurements, and interferometric measurements. Now, we will limit our discussions only to interferometric measurements since it is the best method for quantifying and characterizing color crosstalks. Also, it does characterization at quantization on the microscopic level, so it is more accurate, more precise, and gives us a better distinction with the help of spectral response curves. And now you can see that all the methods which we use to measure crosstalk has to be done before the fabrication of the cameras. Now, why is it so? Because the spectral response curves also depend on the transmission spectrum of the color filters which are involved uh, and the coating of the prism optics, etc. Now, this happens because the cameras which you used, apart from the lenses and the the spectrum which they can observe, it is very much altered by the color filters which are present there. Could be Bayer mosaic filter or other filters. So let's talk about interferometric measurement. How does the setup works and what are the methods proposed in it? So the most popular interferometric method and the latest one is the white light interference microscopy. So since most of the CCD cameras are used in optical microscopic techniques, thus recently WLIM has been implemented to extract multispectral phase information of the light field. So by multispectral phase information means that corresponding to each light channel, it draws a spectral response curve, and with that we can for independently for each channel we can determine what part of which color is going into each of the red, blue, and green channels. So from the fringe projection perspective, we can inculcate this to obtain the wrapped phase map and be able to get a more precise map since the analysis takes place on the microscopic level. Now, white light interference microscopy also provides high spatial sensitivity to the phase imaging due to temporally incoherent nature of white light source. But the problem with this is that whatever the spectral curves that we obtain, they are very prone to noise because of white light noise. So it is same as white noise is more. It is the same Gaussian noise that we have studied. Now the drawback, but people have recently come up with methods in order to remove that white noise with the help of filters, the natural filters. Now this is what the WLIM setup looks like. And as you can see, uh, like the BF1, these are the various kinds of filters which are present there, and these alter the whatever white light is coming from the input side, and which is ultimately in order to obtain a particular color, and we see the spectral response corresponding to the output in the waveguides. So since these waveguides are very sensitive to each of the to the wavelengths of all the three regions, so like the wavelengths of all the three colored lights, that's why they are used for easier analysis and in order to obtain the spectral phase map corresponding to each channel. So with the help of halogen lamp, we either give the red, blue, or green colors, and then ultimately see their spectral uh, the spectral responses corresponding to each channel. Now the interference of each channel of the CCD camera with white light gives us the spectral response curve corresponding to each channel. Thus, we can determine the RGB interferograms separately and analyze them. And after analysis of each channel, we can see the overlap of other colors in the individual color channels. So this is very helpful, since in color fringe projection, in order to do the analysis, we separate the deformations corresponding to each color pixel. So if we since we know that for the camera which we are using, what is the overlap of so consider we are considering the red channel, like if we can see what is the overlap of green and blue in that part of the channel, we can somehow formulate a function in order to remove corresponding to that channel. So for each channel we can formulate functions in order to remove the effects of the other wavelengths, other light wavelengths in the particular color channel. So like three bandpass filters are used in order to see the spectral response curves. There are 460 nanometer, 532 nanometer, and 620 nanometer, corresponding to each RGB sequences. The optical waveguide structure is used since it is very sensitive to the very sensitive to the very sensitive to each of the color spectral responses of the system. Now, if we want to see a flowchart of what is actually happening, we can see it. The interferogram corresponding to a particular band frequency bandpass filter is obtained. Then what we do is we numerically decompose corresponding to each channel what is the part involved in the red channel, what part of the spectrum is involved in the green channel and the blue channel. Normalize the line profiles of the RGB channel with respect to the channel under consideration. Like if we are seeing it for the red channel, then for red, green, and blue channels separately, we normalize the green channel and blue channel line profiles with respect to the red channel, since it is the red channel which is under consideration. And then this normalized line profiles give us a measurement of the color crosstalk in the red channels. Now, with this, what I'd like to conclude is, like we saw in this entire presentation, we saw how the color in included fringe projection is better and more robust compared to phase shifting techniques. We also discussed various methods in obtaining the 3D shape characteristics of an image, were also discussed in detail. We can propose a compact white light interferometric setup for accurate measurement of color crosstalk generated in RGB color channels of a CCD camera. Since the WLIM setup is not so compact, so that is a scope of improvement. Now, the effect of color crosstalk is investigated on multispectral quantitative phase imaging. The 5-step PSA in presence of color crosstalk of CCD camera was also observed. Now, however, the 5-step PSA is not implemented for crosstalk-free multispectral phase recovery of specimen because the accurate estimation is not so straightforward. Now, the next image, so that's my 3D profile, which I generated using 2+1 modified phase shifting profilometry. So this method uses both stereo and structure. So this setup had two cameras and one projector. So it's the stereo plus structured method both. So we can see like some of the details are very fine, like the front part of the, like all the details of the cloths and all, like they are more or less quite the best, I think. These are the references which I used for this for making this presentation. And thank you for being with me.